So we've talked about what the balance diagrams look like for an open circuited, short circuited, and matched transmission line. But there's two more cases we sort of need to talk about. But real quickly, I'll just go through each of these. So for the terminating impedance for the open circuited case, I'll just draw near here. So the terminating impedance for the open circuit case is infinity. For the matched case, it's going to be Z naught, your transmission line characteristic impedance. For the closed circuit case, 0. What the balance diagram looks like for the open circuited case, you'll see a wave that might look like this, like 1 volt, and you'll see that same wave reflected back. For the matched case, you might see like a 1 volt wave launched, and you'll see no voltage coming out. Or well, you'll see a reflected wave of 0. And then for the short-circuited case, let me change the color there. Okay. Short-circuited case, you'll see, if you have 1 volt coming in, you'll see negative 1 volt reflected. Okay, so that's the balance diagram there. The two other cases we need to sort of talk about are what happens when you have an impedance that is, let's call the terminating impedance Z, which I guess I've already done here. But so let's say you have a terminating impedance that's not infinity. It's not an open circuit, but it is still greater than your actual transmission line characteristic impedance. And so you do see an impedance discontinuity. You see a step increase in the impedance. So what it might look like is you'll have like a transmission line, say Z1. That's the impedance of the transmission line. And then there's like an interface, and I'm just drawing that blue line just to show the interface. Then you have a second transmission line, or just a second impedance in general. Just it can be like a change in like the cross section of a trace, for instance. That could be what's represented by this this change in the impedance. And the condition here is Z2 is going to be greater than Z1. So as the wave is propagating in this direction, you see it sees an increase in the impedance. So that's one of the cases we're going to talk about. The other case is where you have an impedance, terminating impedance, that's bigger than 0. So it's not quite a closed circuit, but it is still smaller than your actual transmission line characteristic impedance. So here you have your Z1, you have this next impedance here, Z2, and here Z1 is actually going to be greater than Z2. So as the wave is propagating here, it'll see a step decrease in the impedance. And so that's what this case is. So in the first case, you have Z is somewhere between Z naught and infinity. So it's greater than Z naught, but it's not an open circuit. Here you have Z is somewhere between 0 and Z naught. So it's not quite a closed, not quite a short circuit, but it is not matched. And so those two cases are where reflections become really interesting. So if we're looking at the bounce diagrams for these, I'm just going to draw them bigger. So you have a certain voltage coming in, and I'm just going to label this as we've been doing. So just assume you launch a 1 volt wave as the incident wave. Now the reflected wave you're going to get is going to have the same polarity as the original wave. So in this case, it will be positive, but its value would be less than the magnitude of the incident wave. So I'm just going to write less than 1 volt here in parentheses, just to indicate that. So it's not going to be 0, because we know the 0 is when you have like a matched line. So it's going to be greater than 0, the magnitude of the reflected wave, but it's not going to be quite 1 just yet. And so, like for instance, if you launch this 1 volt into into the signal or into the transmission line, at this discontinuity, you might have a reflected wave of, I don't know, some value, basically just some value between 0 and 1 for this case. And it doesn't have to be, the incident wave doesn't have to be 1 volt. Obviously, I just picked that number because it's nice. But whatever it is, the reflected wave, the magnitude of the reflected wave will be just less than that, but greater than 0. And the polarity will be the same. This is the key thing. When you have an increase in the impedance as you're moving down the transmission line, the reflected wave will have the same polarity as the incident wave. So that's sort of the distinction between this case and the other case here. So if I were to launch, as we've been doing, a 1 volt wave, I'll see a change in the polarity. I'll see an inversion of the polarity, and the magnitude will still be less than the original wave's magnitude. So again, the magnitude won't be 0, but it won't quite be that same 1 volt that we initially launched. It'll be somewhere in between. But the polarity, when you encounter a step decrease in the impedance, the polarity will be inverted. So that's kind of, if you think about this, it's sort of a spectrum. When you have an impedance of infinity, you have the full wave being reflected back. As you start decreasing the impedance, you keep the polarity the same. The polarity of the reflection is the same as the polarity of the incident wave, but you start decreasing the value of the reflected voltage. Then once you have a matched line, the value of the reflected wave is going to be 0. Then you start decreasing the second impedance below the value of the characteristic impedance of the actual transmission line. So now you see a decrease in the impedance, and the reflected wave polarity starts becoming negative. And then finally, you just have the extreme case of just a short circuit. The reflected wave has the same magnitude of, it's equal and opposite, just same magnitude as the original wave, but it's the opposite polarity.